Okay, for the sector area, what's the first thing we need to find? The area of the whole circle, which is going to be pi times 10 squared, or 314 square inches, approximately. So then to find the sector area, it's that area of the whole circle times, perfect, 150 over 360, which is going to be what? 5/12, yep, so 314 times 150 over 360. 130.83. Yeah, because he's dropped the zeros. 150 over 360, it's 15 over 36. I just dropped a zero off of each of them. Saved a couple of keystrokes as well. Yeah. I was just being lazy. Or efficient, depending on who's judging. For the arc length, what do? First step. The circumference, which in this case will be pi times diameter, which will be 20 inches. So 62.8 inches. And then the arc length is going to be 62.8 inches times 150 over 360, which will be 2616. So 2617, how's that? We'll go right in the middle. For a test or a quiz, I will do both the pi key and the 3.14, so anything in between there will be acceptable, just so you know. I've probably said that before. Any questions on those? That didn't work real well. So if I have a circle with a radius of 20 inches, and then a chord that connects the end of one radius to the end of the other radius, and that chord is also 20 inches. And what I want you to find is the area of that little slice, that little sliver out there. It's called, it has a name, it's called a segment. Now, looking at that, is there a way, is that shape there something we can find directly? No. A lot of times you have to find a bigger shape and subtract something out to get what's left over. That piece is going to be what's left over. What's the bigger shape that we're going to find going to be? The bigger shape we're going to find is going to be the sector. We have to find the sector area. Then what are we going to subtract from that sector to get that little piece left over? We're going to subtract the triangle. Very good. Ellipse won't help you. That's not really an ellipse. No, not really half of an ellipse either, because it'd be pointed on the ends. It'd be an elliptoid. An ellipse actually has a very specific set of qualifications to be an ellipse. Now, as we're looking at the sector area, we have one little issue. What are we missing? We're missing the degrees here. but we're not. 60? Why would you say 60? No, you're not wrong. I'm just asking why. Yeah, it's an equilateral triangle. An equilateral triangle, so since all the sides are equal, every angle is 60 degrees. You got it. Now from there, I want you guys work with a partner. See what you can come up with. See if you can get this to work. If you want to partner up or group up, give it a shot. See if you can find that area. Nope. So you guys had this idea of cutting this triangle in half and having to use a squared plus b squared equals c squared to find the height like we did right here. That would work. But there's a different way to find the area of that triangle. The perimeter of that's going to be 20 plus 20 plus 20, which is 60. The semi-perimeter, in other words, half of it, 60 divided by 2, or 30 inches. Therefore, according to Hero's formula, the area is the square root of 30 times 30 minus 20 times 30 minus 20 times 30 minus 20. Otherwise known, it comes out to I think like 34 point something. That can't be right. I'm going to try that again. So it's 30 times 10 times 10 times 10. So it is 173.21. I said 17, didn't I? I was off by a decimal place. 173.21 square inches. You guys all remember Hero's formula, right? Fondly? You weren't even here for it, so don't give me that. Were you here for Hero's formula? Okay. That's right, that was 2 days ago. Okay. That was 2 days ago, wasn't it? Okay, I guess I'll give you that. Now, back up to the sector area. We have to find the area of the whole circle first, which is going to be pi times 20 squared, which is going to be, what, 1,256 square inches? So that means the area of the sector is going to be 1256 times 60 over 360, otherwise known as 209.33 inches squared. So then we got to subtract. 209.33 minus 173.21 is going to give us 36.12. Correct? That is the area of our segment. Not so bad?
Why was the pi times 20 and not pi times 40 when you were trying to find the area of the triangle?
Yeah, area is pi times radius squared. So 20 is the radius, and they had to square. It's 20 squared. If it was circumference, it would have been pi times 40 because pi times diameter. You would have got the same triangle area doing this, by the way. A squared plus 10 squared equals 20 squared. That means a squared plus 100 equals 400. Subtracting 100 gives you 300. A would be the square root of 300, which is going to be 17.32. So you have a height of 17.32. Then you're going to take that times 10 divided by 2 and then times 2, or you just take that times 20 divided by 2, because that'd be the whole base. It ends up being 173.2. Yeah. Make sense? Okay, well, let's try another one like that. Let's see if we can get you guys good at this. What's that? Give you guys a little foreshadowing here. I'm going to call this 15 inches, so another 15 inches over here. I'm going to make this angle here 100 degrees. I do have to tell you that this chord across here is 22.98 inches. So find this segment area out here again, please. Let's see if we're going in the right direction. Let's find the sector area first. So to start, we're going to find the area of the circle, which will be pi times 15 squared. Good, which is going to give us what? 706.5? 706.5 inches squared. So that's if you're using 3.14. The area of the sector then is 706.5 times 100 over 360, which is 196.25. Again, if you're a little off, not a big deal. Most likely round off errors. For the triangle, perimeter is 52.98. Semi-perimeter is 26.49. So therefore the area will be 26.49 times 26.49 minus 15 times 26.49 minus 15 times 26.49 minus 22.98. What's that?
15.26.
Something doesn't work. They can't have the triangle bigger than the sector. Oh, what's that one? 3.51. I get 110.79. So 196.25 minus 110.79. And we get, let's see, it's 85.46 square inches. You'll notice, by the way, the bigger this central angle is, the larger this is. If you've got a really small central angle, there isn't much of a segment out there at all. If you've got a really large central angle, there's a large segment out there. You guys feel relatively comfortable finding those? Like if you had one on a quiz, say in half an hour? Gotta go home, don't feel good. Okay. Now the next little application You'll do something that looks like this. I didn't draw my circle real well, so this is not terribly to scale. But let's say that this chord is cut into sections of 4 inches and 9 inches. This other chord is cut so that this section here is 3 inches. Can I find the length of this section? And the answer is, yes, I can. Within a circle, if we have two chords that cut each other, so that one chord is cut into pieces A and B, and the other chord is cut into pieces C and D, A times B will equal C times D. Every time. So over here, to find this, if I call that X, 3 times X equals 4 times 9. In other words, X is going to equal to 4 times 9 divided by 3. So X will have to be 12 inches.
Always going to be the same way.
Well, if this is 3, yes, it will be. I could move it. Let's see. I move it like this. Yeah, the chords themselves. This is a 3 and 12 make 15. This is 4 and 9 make 13. So the chord is longer. It's just the way they cut themselves. It'll always be the same product when they cut each other. For example, no, they'll always multiply the same total. Like here, let's say this is 6 inches, and this is 6 inches, and this is 4 inches. I know that this here has to be 9 inches. How? Well, what's 6 times 6? 36 divided by 4 is 9. Now this is, 4 and 9 makes 13, 6 and 6 makes 12. The overall chords are not the same, but they cut themselves into pieces that have the same product. Why is that useful? This gets used a lot in construction. Let's say you're doing a doorway or just an opening from one room to the next, and you don't want just a plain doorway. You want to put an arch on the top of it. Make it pretty. Yeah, kind of. Let's say this is a 48-inch opening, and you want that arch to rise above what would normally be the top of the door by 12 inches. What I want to know, now the way you would lay that out is you would, if you extended this circle, pretend that looks like a circle, you would find the center of the circle somewhere, and you would take a piece of string and tie a pencil to it, and you'd swing the string around to make the arch. Or you'd lay it out on the floor and use plywood and cut it out. Cut that out of a piece of plywood and put that piece of plywood in there, right? So you have that arch cut in it. So the biggest thing you need to know is, what is this radius that you need to have? How long of a string do you need to have to trace out that arch, in other words? So let's figure out that radius. I'm going to draw this line in hard across here. This is 12 inches. I'm going to split this into two pieces. In a circle, if a chord is cut by a line at a right angle like that, if that line is part of a diameter, and we're trying to find this full diameter here, so we're going to assume that 12 inches is part of the diameter, it cuts it in half. So if a diameter or a radius of a circle hits a chord at a right angle, it cuts the chord in half. We kind of saw that up here, right? Where are we? If we tried to cut this chord in half, it was going to be a right angle. We assume that because it's an equilateral triangle. That happens for any chord. And the reason that works for any chord is because, well, if I put in these sides here, this would be an isosceles triangle, and since those sides are the same, it's going to cut it in half. So anyway, what we've got there is 24 and 24, along with our 12. What we're going to be finding is the rest of that length. That's going to be x. So x is going to be found by doing 24 times 24 divided by the 12. going to give us 48 inches. So x is 48 inches. That tells us that the diameter of our circle is not 48 inches. What is it? 48 plus 12, 60 inches. So that our radius is 30 inches. So you need a 30-inch string to put that on there and mark it out. Let's say you're making a fireplace. You want your fireplace to be 36 inches across, and you want it to have a height here of 9 inches. Find the radius of the circle that would contain that. Well, we're going to split the 36 into 18 and 18, right? We're going to be looking for this length here through the center of the circle somewhere. What's x going to equal? 18 times 18 divided by 9, which is 36. Very good. Tells us that our diameter is 36 plus 9 is 45. And our radius is 22.5, half of the 45, right? Not so bad? Can't draw the picture? Just don't feel like it? There you go. That makes sense. Let's say you got a large picture window. Let's say that I can draw for a second. 60-inch window for width. The center of that 60-inch window, we have a 6-inch high arc. Find the radius of the circle that contains that arc. Okay, so let's find this. We'll call this x. Pretend that goes to the other side of the circle. So x is equal to what?
30 times 30.
30 times 30 over 6, otherwise known as 150 inches. So our diameter is 156. You look confused. No. So our radius is 78. Very good. Well, we've got 4 or 5 minutes left in our first hour here. I am going to give you a new packet. In this packet, it's actually the 165 through 168. Yesterday, it was the 156 through 157. I wrote it down wrong, but those were the pages yesterday. I still got to get you one of the packets from yesterday. So I'll hand out the new packet here.